presenting today on the robustness of fairness and experimental analysis can help, contribute a little bit to the larger conversations that we're having today on this workshop. So as an illustrating example, let's see, there we go. Okay, so, we've been talking a lot about fairness, as something that, we try to measure. And as an example now, suppose that we are trying to just measure temperature with a regular thermometer, and we take one measurement and we see, oh, it's 25 Celsius, or it's equivalent in Fahrenheit. I keep forgetting the conversion scale. And we could just take that measurement and say, yeah, it's 25 Celsius. There's no doubt about that. But in reality, there are always external factors that can affect the way we're measuring things. Things that we didn't take for granted that, maybe we couldn't have taken for granted, like, let's say the wind. So what should we do then? I think the answer is quite simple. We have seen this, we have been taught this in school, which is just, measure it again and measure it again. And then after that, now we have some sort of idea, we have some sort of range, we can say with some sort of confidence, and as well as, we can measure the type of uncertainty and, the amount of uncertainty that we have around our measurements. So this is a very, long way, and this is a very simple example to say that variation in measurement is quite common. It's something that we have been taught in class, and, it's something that we have considered in other fields. And this kind of variation, we are able to quantify it, and, ideally well-calibrated instruments can reduce it, meaning that a good thermometer should be able to, reduce the variability in its measurements. With this motivating example, I'd like to introduce, the main research questions that we were interested in exploring. The first one being, how robust are fairness measures to fluctuations in the data? How does this compare, to traditional performance metrics, such as accuracy? How do the choices in the model or the data change or affect these trends? And, how are different populations affected? Because in fairness, we tend to, well, one of the main focuses, not the only, but one of the main focuses tends to be seeing how the different effects of machine learning models, affect different populations. And with this in mind, what we present in this paper is that, across 3 different data sets, we look at how fairness and performance are spread. We see how this varies with different kinds of models. And the main findings that we saw in our experiments were that first, the variance in fairness tends to be significantly larger than one in performance. The second is that some fairer models, can help mitigate the spread in fairness, but the variance, the variance being significantly larger than performance variance still remains. And that, generally we see that this variance in fairness tends to be to the detriment of protected groups, the groups that we're trying to ensure that the algorithm does not discriminate against. And, just to start, we can talk a little bit about the data sets that we use. We use Compass, the South German credit data set, and the bank data sets. All of these have been used in the past. So, we're not introducing any new data sets. We just wanted to see with these kind of classic benchmarks, how this variance look. And, the main takeaway from this slide is just that we're looking at a little bit of variability in the data set in terms of size, number of features, the type of sensitive attribute, the type of protected class. We can also look at, their percentages of positive examples, positive protected classes, unprotected classes, et cetera, et cetera. Again, here the point illustrating that, we're looking at a quite different data sets. But then again, these data sets are well-known benchmarks in the field. And with this in mind, we will also be presenting the types of fairness constraints or, fairness conditions that we were interested in analyzing. The first one being equality of opportunity, which I'm sure many of you must be familiar with, but in case any of you are not, the idea of equality of opportunity is to have true positive rate equality between 2 different subgroups. So, in the example of Compass, which is a data set on criminal recidivism in the United States, given that both populations are, going to reoffend, we predict the probability of predicting that they are going to reoffend should be unaffected by race. Another example of, equal true positive rates, for instance, would be with COVID tests. If we have two different populations, the rate at which, we have correctly predicted that someone has COVID, given that they are going to have COVID or that they had COVID, has to be equal across different populations. And the second, fairness constraint or fairness condition that we look into is equality of odds, which is, a stricter version of equality of opportunity. So, we're defining true positive rate equality, but also false positive rate equality across two different populations. Again, in the example of Compass, so we have the same condition as above, and additionally, we also have to have that the false positive rates are equal across different populations. And then in terms of the metrics itself that we are using in order to measure fairness and performance, the first one is accuracy, which had been talked about, which I think most people are familiar with, which is just generally how many of the data points are you actually predicting, both like the positives as well as the negative ones. We also define something called the degree of fairness. This is based on the equality of opportunity. And the idea is just to measure how much do we deviate from that equal true positive rates. And for the degree of fairness, we just switch it up a little, we put an absolute value in there, and all of that is just to make sure that we're looking at a 0-1 scale. So it is a little bit intuitively similar to accuracy, where 0 degree of fairness is the worst, and then a degree of fairness of 1 is the best. And finally, we also look at the direction of fairness or unfairness, where the sign kind of determines which population group is the one being adversely affected. So how are we actually measuring variance? And the main technique here that we're using is bootstrap sampling. So from the test data, we are sampling uniformly, and then we are creating additional tests, bootstrap sample data sets. Where we can, see that theoretically, these are all coming from the same distribution, but there will be little fluctuations in the data. As you can see in the example, we start with the data set where, we have basically the green, the yellow, the red, and the blue, and we sampled uniformly from these, and we get all these different data sets from the same distribution, but with a little bit of variability in it. And the models that we explored are logistic regression, so a very simple model, a model that, has been tested time and time again and again. We also check to see if we impose some post-processing to impose fairness constraints. We also look at these models as well. And we look at different choices in the model, including L2 regularization. So, whether or not we are restricting how complex the model can be, as well as whether or not we can train on that sensitive attribute. So for instance, in Compass, whether we have access to the race of the defendant at the moment of training or not. And the general flow of the experiment is, we start with the Compass, and this is just for Compass, but we do the same for all the other data sets. We start with the data set, we split it into training and testing. For training, we go through the usual procedure of, choosing, our regularization parameter, whether or not we're training with sensitive attributes, whether or not we are imposing some sort of fairness constraint after training, and then we have our trained model. With the test data set, we do our bootstrap sampling, so uniform sampling with replacement. We create 800 different bootstrap data sets, each of them with the same cardinality as the initial test data set. For each of these, we calculate fairness and accuracy. And from that, we get the mean and the variance of the accuracy as well as the degree of fairness. So for the actual results, first we are presenting a couple of histograms. This is just on two different models, one where we don't have any fairness constraints, we don't have any regularization, and we have access to our sensitive attribute. And the other model is one where we have equal odds constraints, so true positive and false positive rate equalities, L2 regularization, and we don't have any sensitive attributes. And these are just kind of to illustrate the general trend that we saw. First here, as you can see in Compass, even just by looking at the histograms, we can kind of already see that the degree of fairness has a significantly larger spread than that of accuracy. Once we impose these equality constraints, we see that the degree of fairness shifts over to the right, where the mean now is a lot closer to fairness, but we still see a little bit more spread than that of accuracy. And across another data set, the South German credit data set, we see a similar trend as well as with the bank data set. And that one, because it's significantly larger, we see a couple of quirks with how accuracy spreads. But generally, these histograms kind of illustrate the point that we see a lot more variance in degree of fairness than in accuracy. And we do F testing to show that this is statistically significant. So the first observation, the one we had already noted, is that fairness variance is significantly larger than performance variance. Now, you can access these numbers and these tables in the original paper, but here I would just like to highlight again, in parentheses, you can see the variances, and you see that it is significantly larger when you compare the degree of fairness variance with accuracy. But we do note that once you have these fairness constraints like equality of opportunity or equality of odds in the second and the third rows, the degree of fairness variance lowers quite a lot. And we do notice this with a couple of with the South German data set as well. But this is not always the case. So I'd like to point out two examples. Here in the bank data set, circle in red, you can see that variance actually increased a little bit when we had equality of odds, but not with equality of opportunity. And an important caveat to note here is also that the degree of fairness mean went up from logistic regression to equality of odds, but the variance also went up. So having higher mean degree of fairness does not necessarily indicate that we're going to have lower degree of fairness variance. And we can see that as well with this when we train with sensitive attributes, the same kind of trends, higher mean, higher variance as well. So this is all to say that fairer models can help to reduce variance, but only to an extent. And this varies depending on the data sets, meaning that as the keynote pointed out earlier, that variance, that fairness depends on the context. We can't just talk about fairness in a very abstract way. We have to ground it in realer concepts. And finally, looking at the direction of unfairness. So again, here we only look at a couple of models, but we can see the general trends from this is that here in orange, you can see unfairness towards protected groups. So each data point in here is a bootstrap sample of the data. And the orange ones are the ones that have unfairness towards the protected groups. The blue ones are the ones that have unfairness towards the non-protected group. So in the case of Compass, African American defendants are the protected group, and Caucasian American defendants are the non-protected group. And before we have a fairness constraint, we see that all of the outcomes actually are unfair towards the protected group. After we have the fairness constraint, we see a closer split to 50-50, but still leaning towards being unfair towards the protected groups. And we see something very similar with the South German data set as well. Meaning that, the third insight that we had is that variance tends to be to the detriment of the protected groups. So, what can we take away from this? Fairness has been, in the news recently, well, not recently, ever since the past 10 years or so, the interest in fairness has exploded. But looking at the intersection of robustness and fairness in machine learning is quite critical, because, if our models are not, if we're not confident in our models, the outcomes, the adverse outcomes, can, have a lot of intersections with fairness and, with the subpopulations that are at risk. As machine learning scientists and engineers, we can take steps to measure and mitigate this uncertainty in fairness. It's just a matter of willingness to put in the time, the effort, and the research to make sure that we can, measure and mitigate all of these things. And finally, we should be wary of claims of fairness without considerations of confidence. Much like, as good scientists, if we ever say something, we should be able to say with some degree of certainty, or, at least mention the degree of certainty that we have about our conclusions, just, to make good science and to make sure that we are doing the best we can to communicate what we know. And that is it. Thank you. And I will happily wait around for any